Hello.
All right, welcome everyone to the Learning About Protocols, the first session, where we are going to be hearing from Rod Allen de Lara and Joan Calope from the Philippines, and they're going to be talking about some pedosphere protocols, and later we will hear from Brian Campbell and Dr. Jinyang Du regarding the SMAP protocols. And this is the first session of learning about protocols. So I'll pass it off to Rod and Joan.
Greetings from the Pearl of the Orient Seas, the Philippines. My name is Rod Allen de Lara.
And I am Joan Calliope, and we're here to talk to you about GLOBE's Pedosphere protocol with emphasis on soil temperature and soil pH protocols. Our presentations consist of 4 parts and will run for 50 minutes. For our introduction, we'll share with you a story about how the Philippines transitioned from being one of the top rice-producing and rice-exporting countries of the world to becoming the world's top importer of rice in less than 100 years. On the second part, we'll talk about the importance of soil, as well as its basic properties and characteristics, and how learning about the pedosphere can bring about real and meaningful change to agriculture and its farmers from a third world country perspective. And on the last 2 parts, we'll show you how you can conduct soil temperature and soil pH measurements following the GLOBE protocol, and how you can combine this with GLOBE's agricultural bundles and other protocols to solve and understand more complex problems. All the informations here, as well as all the photos and graphics that you will see are all properly referenced and cited at the end of the presentation. So let's begin.
In case you are not familiar with the Philippines, we are right there, situated in Southeast Asia. The region is home to some 700 million people. We are a country with 7,100 islands, more or less, depending on how high the water rises during high tide. As of 2020, our country's population is estimated at 110 million people.
To begin our story, let me start by sharing with you this beautiful quote from former US President Franklin Roosevelt in highlighting the importance of soil. He said, "A nation that destroys its soil destroy itself." Now I need you to reflect on that a bit before we move on. A nation that destroys its soil destroy itself. It makes sense, doesn't it?
For most part of the 20th century, the Philippines has been near self-sufficient in its rice production and has even been exporting its surplus production to other countries from 1970s to early 1990s. But fast forward to year 2020, the Philippines is now the largest rice importer in the world, beating China with more than 10 times the population of the Philippines and Nigeria with 2 times the number of people. All that in a span of less than 100 years. Looking back at the same slide as before, we can see that from 1960 onwards, the Philippines has relied heavily on the use of fertilizers to increase its production. Fertilizer use per kilogram per hectare has increased by more than 2,100% since 1960, averaging to about 200 kilograms of fertilizer per hectare by the turn of the century. 200 kilograms is equivalent to about 4 bags of fertilizer per hectares. But the increase in the use of farm input did not correspond to an equal increase in production. In fact, rice yield per kilogram per hectare barely doubled in the same period, which says a lot about the efficiency and effectiveness of use of fertilizers. Worse, the significant increase in fertilizer use also increased the cost of production of rice production in the Philippines. The cost to produce 1 metric tons of rice in the Philippines is 47% and 40% higher compared to Vietnam and Thailand, respectively. This basically reduced the Philippines' competitiveness in the international rice market.
In preparation for this presentation, we interviewed 3 rice farmers from the Bicol region who have been farming rice for the past 25 to 40 years to give us a glimpse of real-world farming in the Philippines. So hopefully after this clip, you would have some idea why modernizing agriculture is easier said than done. In developing nations like the Philippines, where average age of typical Filipino farmer is 57 years old with a 5th grade education and earning less than $6 a day. So without further ado, enjoy the clip. A Field of Dreams.
Ako si Camilo Pitalio, taga La Purisima. Nag-uuma kami sa di. 85 anyos na ako. Nag-uuma pa. Nagkakaumpaman. Pamana ko, mga kagina mo na mag-uma. Kaya minamantila na mo, miski may edad na.
So, ako po pala si Filomeno Bergantin Jr. Kan Zona 5 La Purisima Pili, Camarines Sur. Nasa 56 anyo. Siguro po ako nag-uuma sa presintingon yan na nasa 24 na gayon o 25 araw kaya.
Sir Amoruso, para umasali La Purisima. Wala, edad ko mga 56 na kung wala taon. Lampas tayong taon ng paraon. Kaya ang pag-uma sa pararan, kung magagusi kang dakog, kagusi kang kadikit. Ang pag-umangon yan, magastos na. Bagong araw ka yung panahon na kulang pa kan mga namimirwis sa Roma. Ito, mayong yan na kuhon na yan. Mas kuhan itong mga namimisti. Taon na una, ang patubig migli, desubisindi.
Sa comparison po kan mga previous na pangungumakan sa mga paraoma, nakulaon na maray ang pagkakaiba o diferensya kan mga nainot sa niyan. Itong nainot, kadaklan, pinapaagi sana sa mga natural na mga elemento kan mga paraoma. Sa presintingon yan, ginigibungon yan, may mga artificial.
Pagkakon yan, kuhan mas maral kan mga inot pang panahon dahil adto dawa dikit lang ang nabuno. Ngunyan na panahon na ngunyan ng mga panahon, kunyan. Kasi abono na ang uma. Dahil mag-abono, maluya ang income.
Pag magbase po kita sa ngaran kang pag-a-apply sa pag-uuma, yung pari, ang 1 hectare po mga tulong sako per yan. Ang bawa pagbasag, tulong sako. Pag abot naman sa top dressing, tulong sako man. So, iba pa kayang sabing side dressing, tulong sako magraray kaya balik po. 12 ang nagagamit sa tagabusan bago mag-ani.
Naabot 4 na sako. Hindi kan tubo kan taroy. Para sa sako, gusto kong maka-aw man ko sa yan. Kasi usan tapos para sa akin ko, gusto kong habang nag-uumapa ko, gusto kong makatapos man lang sila kahit makakuha man lang sindang hanap buhay kung sakali sindang magpamilya na. Medyo dahil magkaraan sa iba.
I hope you enjoyed that. Admittedly, the case of the Philippines is a complex one and is a result of many interdependent and interrelated causes such as population growth, weak economic policies, poor planning, and many others. But we cannot deny that among the fundamental causes of this problem, which is often overlooked, is soil quality or the lack of understanding of it. And this is where science and the GLOBE programs come in. Soon the Philippines will have no more farmers left when our aging farmers retire. In the Philippines, most farmers don't wish their children to be farmers. For them, farming is associated with backbreaking work, hard life, and poverty. But science can change that. The problem of food insecurity is not limited to the Philippines alone. In fact, with climate change, things are about to get worse for all of us. In 2021, UNICEF reported that 375 million people in Asia and the Pacific faced hunger in 2020. What can we do to help solve or relieve this seemingly inescapable problem? The answer is to bring science in agriculture and start changing agricultural paradigms and mindsets. The earlier we do this, starting with our high school students, the better the chances we have in securing our food needs in the future.
Just like the water we use and consume every day and the air we breathe, life as we know it cannot exist without soil. Soil delivers ecosystem services that enable life on Earth. It helps purify the water we drink and consume every day. As groundwater seeps into the soil, it is filtered by layers upon layer of soil and rock before it ends in aquifers and then resurfaces to springs, wells, and river systems, ready for consumption. It helps regulate climate. Soil has the ability to absorb as well as reflect heat that helps regulate climate. It helps recycle nutrient back into the soil by helping decompose matter. It provides habitat for many organisms such as bacteria, fungi, insects, worms, and other decomposers that help break down the cells of dead plants and animals and convert them into organic nutrients available for the ecosystem. Soil helps in flood regulation. Do you know that soil can hold between 0.4 to 2.5 inches of water per foot of soil, or 10 to 45% of its weight in moisture? It is no surprise that many places where flooding occurs are also confronted with soil erosion problems. According to the USDA, 40% of drugs behind pharmacies' counters in the Western world are derived from plants that grow on soil. Soil provides foundation for human infrastructure, and it provides with construction materials by which to build those infrastructures. Soil sustains our cultural heritage that bonds societies and communities together, which provides them with a sense of identity. It provides us food, fiber, fuel, and shelter. And lastly, it helps in trapping and absorbing carbon that contributes to climate change. Do you know that a single tree can absorb 48 pounds of carbon dioxide in the air and breathe out 260 pounds of oxygen each year? According to the USDA, one large tree can provide a day's supply of oxygen for 4 people.
But not all soils are created equal. Soil comes in different shapes and sizes. Needless to say, they have varying characteristics and properties. So let's talk about some of these basic properties in our understanding of the soil.
Soils are known to have insulating properties, and its temperature tends to stabilize the deeper you go. Soil temperature has also been observed to directly and positively vary with air temperature, as you see in this graph. That is, if temperature rises, soil temperature also rises, but the rate and responsiveness at which soil temperature changes with air temperature varies with depth. For example, at 0.5 at 0.5 meter deep, soil temperature tends to vary directly with air temperature, but the variation tends to be a lot less than the variation in air temperature. Also, a slight lag can be observed between air temperature changes and soil temperature change. As you go deeper at 1.5 meters, we can still observe the same positive relationship between air temperature and soil temperature, but with lesser variability, and that the slight lag observed previously is a bit more prominent or observable at this depth. This is due to the insulating property of soil. And finally, at 3.5 meters deep, soil temperature changes are a lot more stable and shows less variation over time. As I mentioned earlier, soil temperature remains relatively constant and stable throughout the year. Thus, any significant changes to soil temperature may imply changes in soil characteristics or in its composition, such as changes in the vegetative cover, chemical compositions, climate change, and many others that may require further investigation.
There's a lot of science in successfully germinating plant seeds. The speed at which sprouts emerge from seeds, or the number of days emergence, and the number of seeds successfully germinating is known to be dependent on temperature. Each plant or seed has an optimum temperature by which it shows the highest germination success rate, and the fastest days emergence, as shown in the lower right portion of your screen and shown by the highest green point in the graph. But as temperature goes to the extreme, the survival rate of plants or germination rate decreases, and the number of days emergence increases. For example, onions are known to grow best at 20 degrees Celsius. At that temperature, we expect 99% survival rate of onion bulbs planted in the soil, and see sprouts emerging within 5 days. But if temperature increases, say at 35 degrees Celsius, only 73% of onion bulbs are expected to sprout, and sprouting is expected to be observed within 13 days. On the other side, if onions are planted at colder temperatures, says 5 degrees Celsius, we expect 98% of bulbs to sprout within 31 days. In any case, from the point of view of an onion farmer, planting onion outside its optimum temperature means less profit. The same reasoning goes with parsley, but at 5 degrees Celsius or colder, or at temperature above 35 degrees Celsius, germination or survival is not expected. Here, the optimum temperature is shown in the green cells for different crops or plants. The green cells denote the plant's optimum temperature that maximizes the yields of farmers.
Soil contains a pH level. In simple terms, plant or crops grow best at a certain pH level. At slightly higher pH level, plant growth is stunted. And at even higher pH, it begins to wither and eventually die. The same can be expected at lower pH level. At low pH level, plants show symptoms of nutrient deprivation, such as leaf discoloration, and at even lower temperature, it begins to wither and die at very low pH. What is a pH level? A pH is a measure of how acidic or basic water is. pH is measured from 0 to 14, with 7 being neutral. pH less than 7 indicates acidity, while pH greater than 7 indicates alkalinity. The next slide gives you an idea of pH levels of various common liquids. At the extreme size of the scale, we have hydrochloric acid with a pH of 0 and a drain or pipe cleaner with a pH of 14. Coffee has a pH of 5, while baking soda has a pH of 9. Pure lemon juice has a pH of 2 and soap with 12. Deionized water has a pH of 7, so on and so forth.
How soil pH affects plant growth. Like all living things, plant needs nutrients to grow. Perhaps the three most essential nutrients for plants to grow is the NPK, which stands for nitrogen, phosphorus, and potassium. The availability of these nutrients in the soil, as well as the plant's availability to absorb these nutrients for their own growth, is dependent on the soil pH level. For example, nitrogen is most abundant in soil with pH levels between 6 and 7.5. But as pH go beyond this range, its quantity or availability in the soil diminishes to a point that nitrogen is totally broken down and absent at soil with a pH level of 5 and below, and at pH levels above 8.5. In other words, plants cannot get essential nutrient nitrogen at soil pH of 6 and below or above 8. The same reasoning applies to phosphorus and potassium. But in the case of potassium, its presence in soil is most abundant at high pH level. But the presence of phosphorus at high pH levels isn't necessarily good for plants because at such high levels, nitrogen is lacking. Thus, to a certain extent, one can determine the most suitable type of fertilizer to use given a known soil pH measure. Adding more nutrient in the soil, especially if the soil isn't lacking such nutrient, won't do much good for the plant. Excess nutrient will simply leach out and potentially contaminate groundwater. Aside from NPK, plants also require other nutrients such as sulfur, calcium, magnesium, and many others. The magic word here is balance. That is, most plants need just the right amount of these nutrients in order to grow well. Too much of it is not good as it inhibits the plant's ability to absorb other nutrients. For example, too much magnesium inhibits plants' ability to absorb calcium and sulfur, and too little of it is also not good. So you might ask, what is the ideal pH for plants? The answer is, it depends. Different plants grow best at different pH levels. Some plants prefer very acidic soil, while others have preference for very alkaline soil. Strawberries, watermelon, and eggplants, for example, prefer very acidic soils, while olives, cabbage, and cauliflower prefer very alkaline soils. But generally, most plants grow well in soil with pH levels between 6 and 7. Rice grows best on soil with pH levels between 6 and 6.7.
At the GLOW program, we also collect soil measurements at various depths because different plants have different root systems. Root crops, for example, such as carrots and potatoes, have shallow root systems, while pumpkins, tomatoes, watermelons, and many others have deeper root systems. This is so because different plants have different nutritional requirements for their growth, and some of those nutrients are more abundant at deeper depths. Having given you some background information about soil properties, we're ready to show you how to collect soil data using the GLOW program's soil protocol.
Let's begin with something simple, soil temperature protocol. For this session, we will demonstrate how to calibrate your soil thermometer and how to take soil measurements at different depths, and how to take soil and then give you some advanced tips on how to use star pattern and transect pattern in conjunction with globe soil moisture protocol to answer more complex soil problems. Before you do any of these activities in class, remember to always download a copy of Globe's data sheet and protocol guide. Okay, so let's start.
Let's begin by calibrating your soil thermometer. Always remember to calibrate your equipment before using them. That way you can get an accurate and consistent reading. For this activity, you need the following materials: a dial or digital soil thermometer, a 500 ml beaker, a calibration thermometer, tap water in room temperature, a watch, or a timer.
-23 degrees Celsius and 23 degrees Celsius.
So are you ready to collect soil temperature measurements? For this activity, you need the following material: dial or digital soil thermometer, 12 centimeter nail or spike, 500 ml beaker, hammer, spacer, calibration thermometer, range for adjusting the thermometer, watch or timer, and globe soil temperature data sheet. The first thing you need to do is to place the appropriate marker or spacer on your thermometer that will indicate the depth of the measurements you want to take. This spacer will ensure that you insert your thermometer at the right depth. For example, if you're taking measurements at 5 centimeter depth, you have to measure 7 centimeter up from the tip of the soil thermometer and mark this spot. Measure the distance from the base of the soil thermometer dial to 7 centimeter mark. Then mark a spacer by cutting a piece of plastic tubing or wood to this length. Insert the soil thermometer through the spacer. Label this spacer 5 cm measurement. And similarly, if you're taking readings for 10 centimeter depth, you need to move up the spacer by 5 cm or to the 12 centimeter mark. Again, the 2 cm allowance represents average length of the tip of the thermometer. Okay, let's start, and I'll show you exactly how to do this in the next video.
The time is 3:38 p.m. and the air temperature is 33 degrees Celsius. The soil temperature for 5 cm is 28 degrees Celsius. And for 10 cm, the soil temperature is 29 degrees Celsius.
The soil temperature protocol can also be used in conjunction with the GLOBE program soil moisture protocol using the star pattern or the transect pattern to help you answer or understand more complex soil problems such as the correlation between soil moisture, soil types, and soil temperature. If you're using the star pattern, the temperature probe can be inserted in any of these red circles. In the transect pattern, the location of the temperature probe is shown in red circles here.
Let's now do soil pH measurements. Let's start by calibrating your pH meter.
To calibrate the pH meter, we need a buffer solution with a default pH of 7, beaker, the pH meter, and a timer. Pour the buffer solution into the beaker. Remove the cup of the pH meter and turn it on. Place it in the buffer solution for 1 minute. After a minute, the pH meter should read 7 as indicated in the buffer solution.
Just some fun tips. In case you don't have a buffer solution with you, you can also use liquids with known pH values, such as Coca-Cola, which has a known pH of 2.5, or a freshly squeezed lemon juice with a pH of 3. Using coffee or tea as an alternative buffer solution isn't advisable, given the different kinds of coffee and tea out there, as well as the effect of the type of water being used to brew those beverages. But mind you, the use of these liquids as an alternative to your buffer solution is not recommended for lab quality work requiring high accuracy and precision measurements. But it's always fun to measure the pH value of known liquids.
Now that your pH meter is calibrated, we can now start collecting samples and measure them. For this activity, you need the following materials: soil sample, 3 sampling cups, strainer, distilled water, pen, stirring rod, 500 ml beaker, pH meter, balance, soil pH data sheet, and spade. Okay, let's start.
Let us now collect our soil sample. The pH is 6.5. The pH of sample 2 is 6. The pH for sample 3 is 6.5.
And that's how you conduct a soil pH measurement. The GLOBE program or the GLOBE protocol can be used to understand and even solve real-world problems. For example, the use of pH protocol in conjunction with the NPK protocol, you can determine the optimum quantity and type of fertilizers to add. So no more guessing. You can also determine the most suitable plants or crops to grow at specific soil types, therefore maximizing the yields and profit of farmers. Second, the use of soil temperature protocol in conjunction with the soil moisture protocol can help you determine the most suitable crop and the timing to plant those crops to produce the highest yield. It will also help you understand the effects of soil temperature and moisture on soil development. Lastly, the use of the GLOBE program's agricultural bundle can help you understand complex agricultural issues such as regenerative agriculture, the impacts of anthropogenic climate change in agriculture, acid rain and its effects on crop yields, and many more. And that's it for us. My name is Rod Allen A. De Lara.
And I'm John Calliope.
And we're from the GLOBE program, Philippines, and we are happy to serve you. Thank you.
Thank you.
Thanks so much, Rod and Joan. What a great presentation. We have a few minutes right now. I thought we could maybe take 1 or 2 questions before we go on our break. But I want to also, of course, encourage people to attend the question and answer session that we will be having on Thursday of the annual meeting this week. So it looks like we have one maybe question already from Cynthia. What about natural plants like acorns to oak trees in terms of planting those and understanding the soil types that go into there? That's what at least that's what I'm understanding, Cynthia, from your question. Did I capture that?
Yeah. Well, the basic principle is there. Different plants
That was great.
at different soil types and soil conditions. So if it's easy to know and get information about the type of the pH level at which acorns can grow best and the type at which they can be planted.
What if your soil has heavy metals from the freeway? How can you clean up your soil, or what's a safe way to grow things to eat for your from your garden?
Well, that's a very complex, that's a very complicated and very complex problem, and that falls under the subject of regenerative farming. Of course, there are natural ways to do it, and of course, there's more mechanical means of doing it. But I think the fundamental step is to determine what are those heavy metals present in the soil before you can even figure out on how to safely and effectively remove them.
Thank you, Cynthia. I'll go ahead, Hamid. We'll have that as our last question.
Yeah, that's enough question done. I have a comment. This is the first time I was seeing an art in play in science teaching and education. That's a fantastic choreography. I do not know how much time they put in. Really, I want to appreciate this effort. And it is a very good way to, even during this pandemic time, educators can be innovative. And it's more than an in-person presentation. I was thrilled by each and every slide and the coordination. That was a fantastic effort I want to appreciate. And one more thing I want to say, I know both of them in an Asia Pacific meet. This is a very good example of coordination and collaboration, because Rod is an academic in higher education and John is in school education. This is a good example how people can come together from different, what you call this, the gaps we have of higher to lower. I'm not saying school is at higher education, and this is a fantastic example that is an example and is a testimony to the GLOBE as one of the successful program across the world. And really, I really appreciate the efforts from the Philippines to set a model for others to follow. Thank you so much.
Thank you so much, Mead, for that beautiful comment. And thank you again, Rod and Joan, for your wonderful presentation. I know y'all worked very hard on it, and I know it's very late where you are right now. So thank you for, just thank you for everything that you've done and everything that you continue to do. I know some of your students have been involved as well, so just thank you so much. So for everyone else in the session, we are going to have a break until about 11:15 a.m. MDT, so that's Mountain Time. You can return exactly to this room. You don't need to leave. You can just put yourself on pause, but take a bathroom break. Rod and Joan, if we have to say goodbye to you, I understand if you need to go to sleep. But we will return at 11:15 with a presentation from Brian Campbell and Dr. Jinyang Du about SMAP. So see y'all in about 15 minutes.
Thank you.
Thank you.
Can you still hear me okay, Grace?
Yes, I can see you great.
Good.
All right, I'm going to welcome everyone back. We are going to get going with our second half of this session of learning about protocols. So the first half was really about soil temperature and soil pH and those how those connect to larger pictures. And this is the larger picture, one of the larger pictures that we're going to be connecting those protocols to, which is the NASA SMAP mission. And today we have Brian Campbell and Dr. Jinyang Du to here with us to talk about Pedosphere and the NASA SMAP mission. So I'm going to pass it off to you all. Again, if anyone has questions, please place them in the chat. Thanks.
Okay, thank you, Grace. Once again, this is Learning About Protocols. We're going to be talking about the Pedosphere and the NASA SMAP mission and the SMAP block pattern soil moisture protocol. So I'm going to lead off and talk a little bit about the SMAP mission and the protocol and some of the observations within the protocol and how, when we originally designed this, we designed this to be able for participants to be able to take the block pattern measurements of volumetric soil moisture and compare them to the NASA SMAP satellite data of volumetric soil moisture. And then I will pass it over to my friend and colleague, Dr. Jinyang Du. He is a research scientist at the University of Montana, and he will talk to you more about the science of SMAP and soil moisture and its real-world applications. So we're going to do kind of an expansion of, this data coming from globe and from space, what it can be used for in the real world. So I'm going to start off with a cool little video here, and you may have seen these before. These are called whiteboard videos. They're super short. They're meant for classrooms and also informal education venues. But this talks a little bit about SMAP. This was created when I was the SMAP outreach and education lead back when the mission launched up till several years ago. And we created these whiteboard videos. The folks at the NASA Jet Propulsion Laboratory in Pasadena, California create these. So these are really cool videos. But I'm going to show you this and then get into a little bit more about the mission and the protocol.
Did you know that soil under your feet contains some of the most important water on Earth? And keeping track of this soil moisture is an important mission for NASA. Think of soil as a sponge. It can absorb a lot of water, but will eventually become full, or it can dry out as the water evaporates. Knowing when the soil is getting too dry helps us plan for droughts, prepare for food shortages, and identify places where wildfires can spring up. Knowing when the soil is too wet and can't absorb more rain helps us better predict floods and landslides. The best way to monitor soil moisture is not from the ground, it's from space. So NASA does this with special instruments orbiting high above us. Tracking soil moisture from space helps us improve weather forecasts and climate models. And it helps farmers know when to plant, water, and harvest their crops. Everyone on Earth benefits from the study of soil moisture. It's one case where NASA dishing the dirt is good for all of us.
All right, so that was a little brief foray into the SMAP mission, and it kind of leads us into how we're going to talk about SMAP and the SMAP block pattern soil moisture protocol today. So first off, I may be preaching to the choir here, but what is the pedosphere? It's not a term that the average, global citizen has in their everyday vocabulary. But, when we talk about pedosphere, we talk about soil, lithosphere, all these things. But for our purpose, it's the outermost layer of the earth that is composed of soil and subject to soil formation processes. And this graphic that I have here was taken from a paper, Dent et al. In 2005, where it showcases how the pedosphere is kind of that centralized part, that exists at the interface of the atmosphere, hydrosphere, lithosphere, and biosphere, many of the spheres that we have as part of the GLOBE program. So, and I know Yon and Rod mentioned some of the bundles that their protocols for the pedosphere have been dealing with. Two major ones that the SMAP block pattern soil moisture protocol aligns to within the GLOBE program is the ENSO, the El Nino Southern Oscillation Bundle. You can see here in the pedosphere, it focuses primarily on the soil temperature and SMAP soil moisture. Basically, this whole bundle, this ENSO bundle, is understanding the effects of El Nino and how it affects, everywhere from local environments to global environments, from, helping to understand local weather patterns, and, local environment anomalies in weather. And then we have the water cycle bundle, where you can see in the pedosphere, we have a combination of the SMAP soil moisture, which is volumetric soil moisture, and also the gravimetric soil moisture. That's that standard, soil moisture protocol that the GLOBE has had, pretty much since the beginning, within the last 27 years, it's been in the system. So, but you can see how it also ties in, when you go back to this graphic here, where it talks about being the interface between atmosphere, hydrosphere, biosphere, and lithosphere. You can see here with these bundles, this SMAP block pattern soil moisture protocol really ties into, the hydrosphere and the atmosphere in both instances. So the bundle link is at the bottom. If you haven't ever gone to the bundles, they're really awesome resources that help you tie in and tie together the different protocol observations and how all of these things can interact, showcasing how all these protocols can interact with one another, looking at just your local environment all the way to understanding the global picture. So when we talk about soil moisture, we talk about, lots of things on the planet. You can see here, there's a lot going on this graphic, and you can everything from, parts of the water cycle with precipitation and condensation. You got transpiration, evapotranspiration. You got heat flux. You got all this crazy stuff going on under the ground, from soil heat flux to gravitational flow to interflow. Okay, we're not going to dive into that, but scientists study this stuff for a living. When they study, soils and soil moisture, and scientists who are on the SMAP mission, and as well as Dr. Du, who's going to talk more about this, they look at all of these different variables when they're looking at the global distribution and temporal variations of soil moisture. Okay, they have to know, in order to get these studies right and make this science make sense in the real world, they have to really tie it into how much precipitation is falling to the earth, how much of that precipitation gets evaporated back into the atmosphere. If they know how much water stays in the soil, which is something we can get from the GLOBE SMAP block pattern protocol and some of the other soil protocols, as well as the NASA SMAP, the soil moisture active passive satellite, a combination of these things really helps scientists understand how to apply these results to the real world. So, looking at the SMAP soil moisture block pattern measurement protocol, we don't have the amazing videos that you just saw on the last ones, okay? Because we're as Grace mentioned, we're not focusing specifically on the protocol. We're focusing on the real world, where the first one, they wanted to focus on their protocols and show you how to do them and do them well, which, they achieved that greatly. It was a great presentation, Rod and Joan. But what I'm just gonna give you a little outline here of some of the highlights of the SMAP block pattern, and then show you how we can go on to a site called NASA Worldview and look at the SMAP data, on a big, visualization system. So the SMAP soil moisture block pattern measurement protocol, what it is it's to obtain in situ measurements of soil moisture consistent with the data from the SMAP satellite. Okay, You can see here that SMAP launched on 31 January 2015. We create a global map of soil moisture from this mission about every 3 days. And it looks at the top 5 centimeters of the soil. That's kind of the gold standard, basically where the soil directly interacts with the atmosphere and the environment around it. So we're looking at that top 5 centimeters. So what you have here, these couple images here, are 3 of the major things here. When you set up a site, okay, you're going to create this like 3 meter by 3 meter grid space. And you're going to start, we recommend that you start at, the top left area. And what you do is you basically dig a hole. You have to be careful where you do this. Make sure you're allowed to do this. I work at the NASA Wallace Flight Facility, and they refuse to let me dig on that property because there is still underground ordnance that may be explosive on base. So we are not allowed to dig anywhere on the NASA Wallace Flight Facility. So I have to take it off campus to do this. But make sure everything's good when you're digging. If you're at a school or something, we've actually had someone who got reprimanded by, this was years ago, and I won't name names, but they were at a school and they decided to take their students out to the newly manicured football field and take soil moisture measurement samples. Okay. We told them that is not a good thing to do. And like I said, that was about 5 years ago. So that's all taken care of. It's all good. But they didn't get many holes out there. Someone noticed it. I think one of the groundskeepers saw this and said, you can't dig in the football field. So they had to go another location. So with that said, what you do is you can create, you dig this hole, down to, enough to get this soil can enough to get about 5 centimeters of the soil. And then what you can do either right away or spread it out through the days or weeks or months of the school year. And then what you do is you move 25 centimeters to the right, and then you make another hole. So this is what the block pattern is. It's creating this, basically this sample site where you're really focusing on this. And you can create multiples of these if possible in locations where you might have a different soil type. You might have done the soil characterization protocol to determine what type of soil type. Maybe you have sandy soil in one spot and several meters away, there's actually some loam or, or silt. In my neighborhood where I live in Salisbury, Maryland, in the United States, it's a neighborhood. So they brought, there was soil here. It was basically a sandy soil, but because it's a neighborhood, when they were building, they actually brought in soil. We get all this stuff, on our property. So it's very cool to do soil characterization on our property here. So that's what you do. So then what you do is you place the soil can into the soil. Yeah.
I'm sorry to interrupt you. We lost your presentation.
Oh, okay. Strange. Let me go back. All right. Let me share again. Yeah. All of a sudden it says not sharing. But then I got something, it said, do you want to share as a co-host or a host, which is odd. Okay, let me go back. Let me go back to it here. All right, here we go. All right, can you see it now?
Perfect. Yep, you're good to go.
Okay, great, thanks. So so what you do is you basically, you're going to have to take measurements of different things, kind of like you do with the gravimetric soil moisture, because in order to get the volumetric soil moisture, you're following basically the same idea, the same instructions, but then you're adding something on the end. So for instance, as I mentioned earlier, the gravimetric soil moisture measurement is the standard in situ measurement for determining the amount of water in the soil. This has been with GLOBE for a while. So what we do here is we take the wet mass of the soil, we subtract the dry mass and divide that by the dry mass minus the container mass. That'll give us the gravimetric soil moisture. And then we can figure out what the soil sample bulk density is, which on the GLOBE website and through the the protocol, the data sheets and the actual protocol, it'll show you exactly how to do this. But after you get that gravimetric stuff, you want to do the soil sample bulk density, because you're going to use both of these values to figure out the volumetric soil moisture. So you take the mass of that dry soil, okay, that you got, because what you do for this protocol is you can use a soil drying oven, which aren't cheap. They're $400 to $500. but you could also use heat lamps as well. That takes a little longer. People have actually collected the soil in cans and, realized that you're using a drying lamp that takes a while in a can. So they actually dumped it carefully into a Ziploc bag, flattened it out, closed it up, and basically set the heat lamp, above the bag, so it doesn't have to try to penetrate such a thick amount of soil. So with that said, you calculate the gravimetric soil moisture, then the soil sample bulk density, and then in order to get the volumetric soil moisture, you take that gravimetric soil moisture number that you get, you divide that, you multiply that by the soil sample bulk density that you just calculated. You divide that by the density of water, which is going to be 1, okay, gram per cubic centimeter. So when you do that, I like to think of it as you kill 2 birds with 1 stone. You did the gravimetric soil moisture, you got that, and then you can get the volumetric. Because we're doing that to align to SMAP, because SMAP is looking at that soil moisture in a given volume. Because when SMAP sends off those radar radiometer signals to the earth, you're getting back the soil moisture in a particular spatial diameter, spatial resolution. So you're getting it in a specific area. So, and then you can then compare that to the SMAP data. So I'm going to show you here an example here, and I want to leave time for Dr. Du because he has some awesome stuff he wants to show you. But I'm going to show you this. I'm going to take you quickly to the website. It'll pop right on my screen, and then I'll bounce right back. But an example of how to compare your SMAP block pattern data with the NASA SMAP satellite data. So here is the website URL, and I can put that in the chat then, or if somebody wants to put that in there, that'd be great. It's https and then worldview.earthdata.nasa.gov. And what you're looking at here is you're looking at soil moisture data from SMAP. And this happens to be, as you can see, into Europe. So the reason why on the bottom it says SMAP/Sentinel-1 data, about 3 months after SMAP went into space, SMAP went into space with an active radar and a passive radiometer. And the combined soil moisture data from those gave us high accuracy and high resolution. Unfortunately, the radar on SMAP died in about 3 months, or so, maybe about 6 months after launch. I'm thinking like June or July of 2015, it basically died. So we were getting only the radiometer data for a while, which is, high accuracy data, just the resolution is a little choppy, about I think it was like, Dr. Du can correct me, but like maybe up to like a 40-kilometer, resolution. But with that said, the European Space Agency has the Sentinel fleet of satellites, and Sentinel-1 has an onboard radar. So we have combined the SMAP radiometer data with the Sentinel-1 radar data to get a amazingly high resolution, high accuracy data set, which then can be accessed visually this way and other ways with other raw data and other applications. But this is a way that we can look at it and try to align the globe data with the NASA SMAP data. So what you're seeing here is a combination of 2 things. We have on the left, these are animated GIFs. One is SMAP Sentinel-1 data. And you can see this runs, for a couple of years. And then the same thing over here with the SMAP radiometer data. So you can see that there is, there's a difference in this type of data. You can see it's on the left side, it's very fine-tuned, and we get really, really great resolution here. But the swath isn't as wide as what you see on the right. And you can access all this type of data, different kinds of this data on the NASA Worldview. So I took an example of what I've been talking about, and this happens to be from Croatia, and this is a measurement from the school in Zadar, and I'm going to show you what we did. How you can compare this. So they collected the soil moisture data with SMAP. They did this on January 17th of 2018. Okay. And they got their SMAP block pattern volumetric soil moisture came to 0.37 cubic centimeters per cubic centimeter. So basically what that means is you can turn that into a percentage. So that's about 37%. Okay. So what I did was I went into the NASA Worldview and I found the SMAP data. Now this is what you get. It's not perfect because of the resolution of, you know, the data and when you're zooming down, but we can align it pretty well. So what happens here is if you look here, I got the SMAP data from around the same time on the same day, so 17 January 2018, but it did match up perfectly with this. It's 0.37. SMAP says it's 0.352 to 0.354. And as you can see here, this legend here that this first arrow is pointing to, actually, let me use this here. You can see this arrow that this is pointing to. This basically shows you, you know, when you scroll over, and I'll show you that in the real world, when you scroll over this, it tells you exactly what the soil moisture is in that location. So the latitude and longitude match up with each other, okay? Latitude and longitude match up. And I also should mention, well, I kind of did, that this is an estimation. It's not going to be an exact number, but you can see this is pretty close. And we've had students and teachers from all over. We've had folks like, you probably all know Jody Haney with Bowling Green State University. She and I worked together for a while with her students, and they had about, a dozen SMAP block pattern sites on campus of Bowling Green in Ohio. And they went out and then they did comparisons to the SMAP data as well. And somewhere on the Globe website, there's a report. They submitted it to one of the IVSS several years ago, so you can look that up. But what I want to show you here, and then just after this, I'll pass it over to Dr. Du. I want to show you the, let me see here. Don't need any of that. Guess I don't need that anymore. Wait, I got to go get this back to the pointer. Not sure why this doesn't let me go back to the pointer. Let me know how to get back to the pointer. Usually lets me go right back to the default. Oh, there we go. Let me try this. Nope, doesn't work, but okay. All right, I will jump to that in a second. I'm not sure why it won't let me go back to the default. Highlighter pen. It just won't let me go back to that one. So it is a link there, but I will take you there in a second. So because I want to finish these slides and then I'll pass it over to him. So not sure why that's not letting me get back there. But I want to show you this because this video is something we created called Eclipse. And this is the NASA Eclipse program. And it is a video talking about what is soil moisture and how it applies in the real world. And that'll lead us into what Dr. Du, and you know, I think I'll show on the NASA Worldview because we're going to have that discussion on Thursday, and I can show that directly because I don't want to eat into Dr. Du's time. But I'm going to show.
Slide, right?
What's that?
We can't see anything on your screen.
I'm not playing anything yet. Sorry.
Oh, you're okay. Sorry.
Yeah, I'm about to start the video. Sorry. So I'm going to show this video and then we're going to jump.
We learn very early in life how the weather affects the way we dress and even when some of our favorite foods are in season. As we get older, we carefully watch the weather and climate models or flood and drought predictions to see the potential impact on our wallets. Whether it's knowing when to bring an umbrella or when to conserve water, we're always looking for better ways to improve these models. But how do scientists come up with these complex predictions, and how is math involved in the process? The answer could be beneath your feet. Find out more next on Real World. The layer of soil just below your feet and the moisture that's trapped there hold the key to understanding the connections between water, energy, and carbon cycles here on Earth. And NASA's Soil Moisture Active Passive mission, also known as SMAP, will help scientists to find that key. SMAP will measure soil moisture across the entire globe and determine whether the moisture is frozen or thawed. But what is soil moisture and how is NASA going to measure it?
Soil moisture is the amount of water that's in the soils. So think of soils as a sponge. So sponges can hold water up to a certain point, then they saturate. So soils are sort of similar. They can hold a certain amount of water.
NASA has a mission that is going to be launching called SMAP. SMAP is the Soil Moisture Active Passive mission, and it will be measuring soil moisture from space. Because when we measure soil from space, we can cover a lot of area in a short amount of time. we will have a global map of soil moisture every 3 days from SMAP.
So that in itself will feed into a number of applications. It'll feed into weather models, climate models. It'll feed into flood modeling, drought monitoring models. It does have a lot of applications.
So soil moisture is simply the quantity or amount of water contained in a given sample of soil. How will SMAP be making these Earth measurements from space?
SMAP has two sensors. They're both in the microwave range. It allows us to see through clouds. So regardless of day or night conditions or any kind of weather conditions, we can still see the surface of the Earth.
SMAP is an active passive mission. The active, or the radar, is going to give you high resolution. So it's going to give you a lot of detail within a 3-kilometer resolution. And then the passive, which is the radiometer, is going to give you high accuracy. And that is going to give it to you within a 40-kilometer resolution. What the SMAP scientists are going to do is they're going to use math. They're going to write an algorithm to essentially combine the 3-kilometer and 40-kilometer to give you a 9-kilometer high accuracy resolution. So within that 9-kilometer grid space, you will have an understanding of how wet or how dry the soil is.
To help you think like SMAP scientists, try measuring the changes in soil moisture in your own backyard, because different kinds of soils hold different amounts of water. You may wish to take several soil samples from different locations. Take a sample of soil from a depth of 10 centimeters. Measure 100 grams of soil using a balance scale. Be sure to remove any rocks and pebbles, as well as any worms or insects from your sample before you measure it. Place the sample in a location to dry. Each day, for 10 days, record the mass of the soil to the nearest tenth of a gram. Graph your results. How did your sample change over time? Did you notice any patterns? To calculate the percentage of soil water in your sample, use this formula. The percentage of soil water equals the mass of wet soil in grams, minus the mass of dry soil in grams, divided by the mass of dry soil in grams, and times 100. Similar to the measurements you made, SMAP will collect global measurements of soil moisture, resulting in a global map of soil moisture every 3 days. Having that constant stream of data will allow scientists to accurately track how soil moisture changes in a particular location. And just what will these measurements help us understand?
The soil moisture, knowing that, it will actually tell us a number of things. So depending on what you're looking at, and if we were to look at flood modeling, how far out the flooding waters could essentially go, depending on how wet the soil is before the storm or before the flood really picks up.
SMAP will advance our ability to monitor droughts and predict floods, and this helps to mitigate the impacts that this might have on human lives.
For crop production, agricultural productivity, crop productivity, even crop forecasting and having an understanding of when to plant and when to essentially harvest your crop.
Being able to have an assessment on whether there's a drought coming on will help better manage crops and better estimate what crop yields might be like.
It's critical for agriculture, it's critical for health. So it does play an important role in our day-to-day lives.
With SMAP, returning global measurements of soil moisture every 3 days for at least 3 years, scientists will have a ginormous amount of data that has real applications for each one of us here on planet Earth. See you next time on Real World.
All right, so that leads us into Dr. Du. He's going to talk about some of the applications with SMAP soil moisture data, and he'll be covering, some of the awesome science research that he has done with soil moisture and soil data. So I will stop sharing and pass it over to you, Jin Yang. It's all yours.
Thanks, Brian. I'm going to share my screen. Great. All right. So thank you, guys. Thanks, Brian, for the wonderful introduction of soil moisture protocol and NASA SMAP soil moisture products. Now we know what soil moisture is and how to measure it from ground and also from satellite. Then we can what we can do with this data. As we know, our Earth's water cycle is a dynamic system with soil moisture and other components closely interconnected. Here, I will focus on water, including both soil moisture and surface water. Once we have the surface water information, we can go a step further and know if there's too little or too much data, or too little or too much water in plant, soil, and land surface, and help to improve agriculture, water resources management, and fighting extreme events such as landslides, droughts, and floods. However, we need to bridge the gap between measurements. Here, the satellites are representing measurements, and the applications such as these flood or drought monitoring and forecast. And the key of this bridge is radiative transfer theories or remote sensing theories and artificial intelligence. All right, let's take a more in-depth look at how the SMAP data can be used for floods and droughts monitoring and forecast. So globally, climate extreme events caused more than 100 deaths and over 200 million USD dollars in losses every day on average from 1970 to 2019. Flooding is one of the most widespread and costly natural disasters. In our warming world, intense flood events are expected to be more frequent. It's crucial for us to have the capabilities for all-weather flood monitoring and rapid near-term flood forecasts so that we can be better prepared. So here is the question: can we develop new capacity for mitigating flood risks over the world using this wonderful global satellite data? As I mentioned on the first slide, we have two powerful weapons to fight floods and droughts. One is the remote sensing theory, and the other is the artificial intelligence technique. Here, I would like to give some background details about satellite remote sensing of surface water. The figure on the lower left here, this I think Brian's video also shows something like this. This figure showed the electromagnetic spectrum. For satellite remote sensing of Earth's surface, we can use this visible or infrared and microwave observations to distinguish water signatures. So actually, the optical remote sensing is natural to us, since the optical sensors are just like our eyes, which see things, which capture the visible lights, and that can be used to capture images and distinguish objects. The optical sensors can detect an object with the sizes from sub-meter to a few hundred meters from space. For example, the NASA USGS Landsat satellites have recorded our Earth's surface at 30-meter resolution for multi-decades. However, these optical sensors cannot see through cloud or detect water and vegetation. So that's why scientists also use microwave sensors such as SMAP radiometer to observe the Earth with all weather and day and night capability. So as you can see, these different types of sensors are just like our human beings, which are not perfect. So we need to use the complementary information from this multi-sensor satellite data to provide advanced global monitoring, which can be benefited from SMAP and other type of sensors. Working them together, we can see different resolution and at different cloud or atmospheric conditions. All right, so here are some examples of what we do using the different sensors. As we can see that we can map the extent of rivers, lakes, and the flood inundation using these different type of sensors. Either the first one is from SMAP, or the second one from a little bit higher frequency microsensor called AMSR. And the third one is a well-known optical infrared sensor called MODIS. So either type of sensor can provide the global mapping of water distributions. And you can see they are highly correlated in the spatial patterns, very consistent. However, if you see closer, the lower, okay. If you can see closer, the upper left figure, which is from SMAP, shows more water signals than the higher frequency AMSR2 and the optical error models results. This is because SMAP has a lower frequency, which means it has better penetration ability. Then it can not only detect open surface water, but also water and vegetation, even for water for the flooded forest. And it can also provide 1 to 3 day repeat observations of the whole Earth. That means it can capture the water dynamics in a more timely manner, so that we can have this figure D, which is the SMAP captured flood inundation seasonal variation. And this figure shows that the seasonal variations captured by SMAP are consistent with the characteristic seasonal wet and dry cycles. And also the anomalous flooding patterns is similar, is consistent with that observation period, which is characterized by the ANSO activities. So there are, for example, dry events in Central Asia, and sorry, this is a wet event in Central Asia, and also the flooding events in Lower Mississippi. Let's go to the next slide. Now let's take a look at the SMAP flood mapping results for some extreme events. Here, the first extreme event I would like to focus is the Hurricane Harvey event. Hurricane Harvey was a devastating Category 4 hurricane that made landfall on Texas and Louisiana in August 2017, which caused the catastrophic flooding and more than 100 deaths. Widespread flooding can be seen here in the Houston area on August 27th. So here, the figure on the left is what SMAP captured of this wide spread flood event. And also we can see flood water around Houston has substantially receded by August the 31st, which is the middle figure. And so on the right, when we do the difference between these two figures, we can see the change in flooded areas between these 2 dates. So using SMAP, we can capture this the whole process of this flood event. So let's not only focus on the US, but also another extreme event which occurred in Africa. The historic tropical cyclone Ida event is one of the most devastating cyclones affecting Africa in decades. It brought extreme rainfall and flooding to South Africa in March 2019, and caused damages exceeding $1 billion with severe losses of life and infrastructures. Surface flooding from Cyclone Idai, which made landfall near Beira here, Mozambique on March 14th, 2019, had brought heavy rain to the region, which was observed by SMAP. So we actually recorded the pre-flood surface inundation level, the peak flood surface inundation level, and the difference between these two figures give us a clear idea of the flooded area. And we can see that the flooded area increased between the 2 days, and the Beira region was mostly hit by this cyclone. So this is the same thing, but we show this in an animation. So this animation gives a more complete view of this flood event. It shows the changes in flooded areas over the Southeast Africa during this flood start, peak, and recession periods. However, the spatial resolution of SMAP is about 36 kilometers. Though we have the enhanced resolution product, but the original resolution is about 36 kilometers. It's more interesting to know if a specific location, for example, a house, is flooded or not. So can we do something to improve the spatial resolution of the resulting SMAP water maps? Can we borrow the fine scale details from the optical sensors? The answer is yes. For example, here we developed a downscaling approach to merge SMAP water maps and historical observations from Landsat for generating 30-meter water and land classifications. As shown here, for different locations in the US, the downscaled results are highly consistent with the actual Landsat observations. So this is one approach. We borrow the optical sensor information to do the downscaling. However, remember this is not the direct observations from the optical sensor, but the past information provided by Landsat. So besides the downscaling technique, it will be more interesting, or we need some more powerful tool to capture the fine details of flood inundation by direct observations from the satellites. So here we rely on the active radar sensors. We call this SAR sensors, synthetic aperture radar SAR sensors. So as you can see here, for this EDI event, there are no optical observations during that period because of thick cloud. However, since we have this Sentinel-1 SAR, and we can detect the water inundation changes during this flood period. And similarly, we can see this huge widespread flooding areas in another region of Mozambique. And all these were captured by this Sentinel SAR sensor. Okay, the above results demonstrated how different satellites are capable in mapping flood at regional and even household scales. However, this is not enough. It would be more interesting and useful to know if a house, school, or farm will be flooded or not due to a coming storm. So the question now is if we can do both flood forecasts and near real-time inundation mapping. The figure here illustrates the overall idea. As you can see, a machine learning component here. A machine learning component was added to the satellite remote sensing for achieving flood inundation forecast. The combination of satellite data and big data analysis will help us to forecast flood hazards up to the household level. So let's see what we can do for the flood forecast. To do this, we developed a machine learning approach within the Google Earth Engine framework. So this framework will help us to do 24-hour and 72-hour flood forecast, as well as 30-meter inundation mapping using observations from multiple satellite sensors, which include SMAP, Landsat, and we also use the rainfall forecast from NOAA GFS. Here, I like to recommend Google Earth Engine to students. Since Google Earth Engine is kind of open to everybody, it's a really powerful tool. It has many remote sensing data sets there, so you don't have to download data. You can just use their data archive. And also, you can access many coding environment, including Colab or the Google Code Editor, which is kind of JavaScript environment. And you can just use them and a lot of libraries, such as machine learning libraries, similar to me, to do this forecast. And here, the assumption of our forecast is that rainfall is the primary driver of flooding, and that rainfall and flood relationships are consistent between the past and the forecast, so that we use machine learning to learn from past and do the forecast for the future. So we applied the train model to 2 dates for the EDI event. One date is the flood peak date, and the other on the right is the flood recession period. And as you can see, that comparison with the actual radar observations, we show similar patterns. For example, here on the left, the flood inundation prediction on the left show widespread flooding in the north, similar to what observed from SAR. And when for the March, for the flood receding period, we see most flooded areas remain in the northern and the southern areas, and the prediction and the satellite observations are consistent. Okay, so we integrated these two tools, both flood mapping and forecast tools, into this small app. And you can see that the left one is what SMAP showed, the flooded areas, and the right one is the 30-meter resolution details. And they have different layers, including the near real-time mapping and also the forecast layers. And based on this, you can easily check where is flooded or where will be flooded. Okay, now let's change the topic a little bit. So we are not only focused on flood. The satellite data are also quite useful for drought monitoring. As we know, as the projected global warming continues, more frequent and intense extreme events are expected. Actually, for this year, we can feel the heat wave from time to time. We can see drought events in many parts of the world. So it's quite an important critical issue for us to monitor drought, and this is very important for food security issue. I think this is particularly important for this year, food security. Here below, I showed two figures showing the global drought conditions for a recent period of this year, and the left one is using the multiple frequency microsensors called AMS2. I mentioned this earlier. And the right one is using the NOAA optical sensor. And the left one showed the drought conditions, and the right one showed the vegetation water stress conditions, which is kind of equivalent to the drought conditions. And they can both give you different aspects of droughts. So the key for doing this drought monitoring is that we need the long-term satellite observations. So by using these long-term data products, we can derive the anomalies. So which part is not normal compared with the past. And using this anomaly information, we can check the drought conditions. We can even get drought conditions in terms of different water components. For example, here we see the soil moisture anomaly, we see the water pressure deficit anomaly, and we can also see the surface water inundation anomalies. So these give you different aspects of descriptions of the drought. Similarly, we can also use SMAP. It has a limited period of time of observation. However, it still gives you the description of the drought condition. And the SMAP map, drought map is consistent with the baseline USDM result. So that means independent satellite observations can give us valuable information for doing this drought monitoring and perhaps also forecast. So we actually did this test to see if we can do this drought forecast using the satellite data, in particular using the SMAP data. And this is an example. So we developed this a deep learning framework to learn from the historical time series for predicting for the future. In our result, the deep learning model framework trained to forecast future US drought monitor categories up to 12 weeks into the future. So that means we don't have to wait for the USDM result. We can know the future 12 weeks before. For example, here, the 11-week ahead forecast on the left was found highly consistent with actual US drought monitoring result for a recent drought event in the Western US. And for these drought predictions, the satellite observations and products, including the SMAP soil moisture, are among the most important predictors. So here, it demonstrates why we need SMAP, why we need soil moisture, because it's really important and really useful for flood and drought monitoring. All right, I guess I don't have much time, so let's do the summary. In this talk, we see the importance of using different types of satellite sensors together. And we also see the powerful tool of machine learning to integrate these different type of information together to do effective regional flood and drought monitoring and forecasts. And we can also see that the in situ soil moisture measurements are quite important to link these applications. So as we know that, I would say the bottom line is that we need to understand that Rome was not built in a day, and all these fancy applications were actually built from this ground-based sampling. And also it was built from satellite observations. As we do more ground sampling, know more about these protocols, and do more understanding of the interconnections among different variables and processes of this Earth system, we can build a better system to fight against these extreme events. Okay, so here are a list of the dataset and app links. If you're interested in, you can check these in details. And if you have further questions, please contact Brian or me. All right, thank you very much for your attention.
Thank you so much, Dr. Du. Really detailed presentation about how SMAP is used by scientists and how that data is continually being used with other sensors. So thank you so much. And just also the connection that Globe is collecting data that's supporting all of this work, which is really, really neat. Thank you, Allison. You may look into the chat, everyone. Allison has added a few other additional resources. So these are really good. Actually, Allison, I'm going to take these and add them to the chat in the platform as well. These will be great in conjunction with the one-pager that we have. So I encourage everyone to go to the files and look at the one-pager where you can get even more information about SMAP, about the different Pedosphere protocols, and how to combine them with other classroom activities. So I've added that to the other chat so it will live on as well. I'm going to unspotlight. We have a little bit of time, so if folks have questions for Dr. Du and Brian, I encourage you to ask them. We could probably answer maybe 2 questions here, but then I will encourage everyone to come to the question and answer session that, again, is going to be happening on Thursday of this week.
Yeah, can I?
Lots of good compliments right now. So sorry, Brian, go ahead.
Yeah, so Dr. Allison Leidner put in here, about, there's lots of choices in NASA worldview looking at soil moisture. And since we're focusing on SMAP, and if you scroll back into the chat, I added the 2 that are the best ones that we use to do comparisons. You can see that in there. And as I mentioned before, on the Thursday Q&A, if anybody wants me to, during that session, go in briefly to worldview, or you can contact me directly and we can do it, somehow. I can show you how to easily access that, but it's just, it's pretty simple to do. But once you know how to do it, it's, pretty self-explanatory.
Perfect. Thank you, Brian. Would anyone like to ask any questions at this moment?
Or come up with some stumpers for Thursday.
Well, you'll have time to digest more of the information as well. I did get a question. The recording of this session will be available at the end of today, at the end of, close of business for Mountain Time. So it should be available there to review or to download, and it will be available on the platform for up to a year. So please feel free to go and rewatch all of these wonderful recordings. Todd, you asked where do we find the recordings? They'll be found right where you came to enter the session. So that join meeting button will be replaced by actually a video window, and you'll be able to just press and watch the video like you're in a YouTube channel. All right, well, I'm gonna let everyone go. It's lunchtime here. I bet people need some snacks or some sleep. So thank you all so much for coming to this Learning About Protocols session. This is a new format we're doing this year, so we'd love your feedback. I encourage you all that participated today to go to the polls function within the virtual platform, and please answer a few questions. We'd love to just get your feedback and know if you enjoyed this presentation. So thank you so much. And again, a big thank you to Dr. Du, Brian Campbell, Joan Calope, and Rod Lara from this morning. So thank you so much. Bye, everybody.
Thank you and bye-bye.